trendsetters, welcome to today's Grade 12 Physical Sciences show. Today we have a special revision lesson on chemistry. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Question number 1. It takes us from a prelim paper written in Gauteng in last year, and it gives us this picture. I just want to make the things a little bit bigger. We're told that we've got chlorine gas over here, going in over there, and in this solution we've got sodium chloride. That's in aqueous solution. There's a salt bridge, and over here this is a tin electrode. SN is tin. Even if you didn't know it was tin, doesn't matter. This is SnCl2 aqueous. Okay, we know that there's a salt bridge. There's the voltmeter, and the salt bridge connects the two in half reactions. Now, there is a line over here which I just want to highlight and make it a little bit clearer. This line, and I don't want the arrows on it, so I'm just going to remove the arrows. I'm going to make it like that. That line is said as an electrode A, so that you can see this is electrode A. Right. Now, when you're given something like this, you've got a salt bridge in place. One side has got gas bubbling through it. The other side is a solution with a metal inside it. You know that this is a galvanic cell. It's just like the one that we did in our example. It's like the zinc copper cell. And so we know it's a galvanic cell, and we're asked to write down what is the energy conversion that takes place in the cell. Galvanic cell, we've got chemical potential energy. So chemical potential energy, and it gives out potential, it creates electrical potential. And so that electrical potential can be used to drive a current, and that's why we've got, in a closed circuit, we can get potential energy. So from chemicals, we get electricity. What's the other way around? Well, that wouldn't be a galvanic cell, that would be an electrolytic cell, where we use electrical potential to force a chemical reaction to take place. This is the natural occurrence. It happens spontaneously. When we put reactions together, some things are more reactive than others. You get some strong reducing agents, and some that are weaker oxidizing agents. You put them together and they will react spontaneously. You don't need to add any energy. That happens in a galvanic cell. Okay, let's move on. Now, the next thing, we're dealing with these gas electrodes, and it says to us, name a suitable material that can be used as electrode A. Now, if I look at electrode A, I'm seeing that the gas that is bubbled in is chlorine gas. Now, what do I know about chlorine gas is that it's highly corrosive. So I don't want to have another reaction happening there. I want something that is more neutral. And the most common electrode for a gas electrode is the platinum electrode. So I would go for platinum. It is expensive, but in industry it's used quite often. An alternative would be graphite. And graphite isn't going to be corroded much by chlorine. So the next question, let's move on. It says, is electrode A positive or negative when the cell is working? Now guys, this takes us to the nub of the question. This is the really important part. We've got to decide what the things are in the two half cells and what they're doing. So at the moment I haven't even begun to answer it, but I'm going to start working out the reactions that are taking place. And fortunately for me, and for you, on the data sheet, in your matric exam paper question, you will always be given 2 tables of standard electrode potentials. This ranks the reactivity of the different substances in order from high reactive, good oxidizing agents, good reducing agents, and it puts them in order. Now, there are 2 tables. I'm going to use table 4B, and I'll show you exactly what that is. You might have been shown 4A in your textbook or in your class, but I like to use 4B. And the reason is, it doesn't really matter which one you use, but I'll give you a reason why I like this one. If we look at this, and there's some writing that I haven't included on the side, it tells us that these at the top here are on the right-hand side. And on the right, we've got reducing agents. Okay. And the ones that are at the top are the strongest. So that's how I remember. The strongest, where I've got lithium at the top, it's on the right of the arrows, and it's the strongest reducing agent. At the bottom on the left, you can always find it. The bottom on the left, you've got fluorine. Wherever you are, you must know that that fluorine is the strongest oxidizing agent. Oxidizing agent. So you need to work with that. If it's the other way around, fluorine's at the top, they give you the table with fluorine at the top, then you're going to have to work with it. But normally you've got a choice. Now there's something I want you to see about this. Notice that the strong oxidizing agents have a big positive value of E0 or E cell, and the ones that are strong reducing agents have a negative value. So the strongest reducing agents, the bigger the negative value. And that kind of makes sense. The more negative something is, the more able it is to donate electrons. The more positive it is, the more willing it is to donate electrons, negative. When it's positive, it wants to take electrons to become neutral. Now, on this table, although it's very long and you can't see the whole thing in one go, in the middle, over here, we've got the hydrogen standard electrode. And it's noticed that that is 0, a value of 0,00 volts. And we use this measure to compare everything else against it. So we need to have 2 things that react. We want something that's going to take the part of a reducing agent and something that's going to take part of an oxidizing agent. Now, in our reaction, what did we have? Let's go back to the question, and you'll see that on the half cell, we had chlorine gas, and it became a chloride ion. So we're going from chlorine to chloride. That's my little interpretation of it. Plus 2 electrons. And on this side, I've got zinc, sorry, not zinc, but tin, and I'm going to do it in a different color. I'm going to say tin has gone to tin 2 plus 2 electrons. I don't know which one of those goes, because remember, these are reversible reactions, and it could be either way. We don't know the competition yet. Let's go and check on the table. So we've identified that we've got tin chloride here. Does chloride have anything to do here? No, because there's no chloride there. So it was definitely the tin that was reacting to produce the tin in solution. It could have gone that way or that way. We're not sure. The chlorine could be making chlorine gas, or it could be making chlorine ions. We don't know. But let's go and compare now on our table. So let's see, what's the relative position of tin and chlorine? So the way I do it is I start at the top and I move down from the right. And I'm looking for SN, my tin. And there I found it. You see, it's the first time I see SN, and that is your equation. So we know that that's the reducing agent. Notice we haven't seen, if I move my finger down, any sign of either chloride or chlorine. There's nothing, no chloride, no chlorine. The first one that I've come to from the top is tin. And it has a number associated with it of minus 0,14. Now, if I carry on down on the right-hand side, I will eventually get to chlorine down here. But what I want you to do is rather in your head follow this rule. We're going to write that equation down. Then we're going to go down on this side. We're now looking for the oxidizing agent. And we go all the way down until we find, there we've got it, chlorine. And can you see the shape now that I've made? Hopefully you can. The blue line went down like that in an anti-clockwise direction, and it's made the shape of a C. Okay, we had our tin over there, and our chlorine over there, and our chloride is being formed over there, and our tin 2+ is formed over there. So we must bear that in mind. So we now know that tin is the reducing agent. It's where oxidation is going to take place. That is the anode. This is where we are gaining electrons. It's the oxidizing agent, and it's going to be a reduction reaction, so it's the cathode. See, all this little piece of these bits of information are going to help us answer the question. You need to be thinking it through and making sure that we answer. Right, let's go and see what happens. Go back to our question and see if we can answer it now. What was the question? The question said, is electrode A positive or negative when the cell is working? Well, we've just established that we're going to take the chlorine and it's going to gain 2 electrons and it's going to form chloride ions. That was from our half reaction sheet. We saw it in that C picture. The chlorine gas gains 2 electrons to form chloride ions. So now if it's gaining electrons, guys, here's the trick that I need you to understand. If it's gaining electrons, what are electrons attracted to? Electrons are attracted to something that's positive. So this must be the A must be positive. Must be the positive electrode. Why do I say that? Well, you see, at the other electrode, let's just argue it through. What's happened is the tin has donated electrons. Electrons have moved from here. Electrons are moving to there. So where electrons move from is the negative electrode. This must be the positive electrode. Electrons are attracted to the positive. The source of electrons are going to be negative. So that's why this is negative, this electrode is negative, and that electrode is positive. Got it. Let's move on, because I think we've got most of the things sorted out now. Next question says, write down the formula of an ionic compound that can be used in the salt bridge. Now, the salt bridge needs to allow for movement of ions. As much as electrons moved in the negative in that direction from the anode to the cathode, and you need to understand that, the salt bridge helps negative ions move from the cathode back to the anode. And so we need something that's not going to clog up, that's not going to precipitate. We need something that's highly soluble. And the preferred substance is potassium nitrate. Now, notice it said write down the formula. So I can't write down in words potassium nitrate. I must write down the formula KNO3. Okay, next part of the question, go to another slide, and hopefully we'll sort things out. In which direction will electrons flow in the external circuit? Well, we've answered it already. We've already established that the tin is the anode, so it's going to form, it's going to undergo oxidation at the anode, so it's going to be from the zinc, from the tin, sorry, from, we must write down from the electrode A to there, or from tin to electrode A. I'm going to choose the second one. From tin to electrode A. Now, we've got the next question, which I absolutely love. This is an amazing question, and I really want you to get it because it's so important for us to understand. It says, in which direction will each of the following ions present in the salt bridge flow? Only write down towards the tin. Sn is tin, Zn is zinc. Tin half cell, or towards the chlorine half cell. So now, what are anions? Anions are negatively charged ions. Negative ions. Now, what are the negative ions that we've got in the solution? Well, remember in the salt bridge, we would have the nitrate ions and we would have chloride ions. Those are the negative ones. So over here, look what's happening. Let's just write this out so we've got it. Chlorine goes to form chloride ions, 2 of them, plus it gains electrons. Okay? The chlorine's gained its electrons. Is that right? Sorry, I've got it wrong. I've written it incorrectly. It must be on the other side. Chlorine gains 2 electrons to form chloride ions. That's right. So the chloride ions, we've got more of them here. Now, initially when we started, we had the same number of sodium ions and chloride ions. Now the cell's going to quickly give up working if there's not a path for that extra chloride ion to move across. Fortunately, there was the same number of zinc ions and chloride ions in this solution. They were the same number. Even though the charges are not the same, for every one of these, there were 2 of those. Now, if we take one of these away, if we take one of, if we take one of the zinc, the tin ions away, we take one of those away, what are we going to need? What are we going to need? We're going to need, let's just take that away for a minute, we're going to need a partner. We're going to need a partner for these. So where's that partner going to come from? Remember, we've got extra ones of those there at the moment because we are taking the chlorine gas is forming chloride ions, and here we've got a problem. We're wanting to have some more positives here. So what's going to happen? We're going to have let's just see whether I've got this. I really think that I might have been doing something wrong here. No, I've got it right. I've got it absolutely right. And what we're saying is I didn't write this equation down. Tin goes to form tin 2 plus 2 electrons. Remember, the electrons are going that way, so it's not going on to there. It's making some extra ones. So I had it right the first time. The chloride ions are going to come along, and we're going to get 2 chloride ions for every extra one that we've got into the solution. So the anions are going to move which way? Towards the tin half cell. Now, what about the cations? Guys, here we've got a problem. Let's see what the problem is. Where's the imbalance? We had too many chloride ions there. Remember, we had too many chloride ions there because all the time we were making chloride ions. And so we had too many. We had to give them up. We've got too many here. So we haven't got enough of them here. So we've got to have to move them across so that we can get more partners in. Now let's look at the cations. Here, we started off with an equal number of those and those. Equal number. Positives are all fine. Here we've got an equal number, positives and negatives there like that. So now, what's going to happen? I'm going to get more chloride ions. More chloride ions because of this reaction up here. Go back to it. This reaction is giving me more chloride ions. So I've got an extra chloride ion. If I've got an extra chloride ion, how am I going to neutralize it? Well, I can't use the tin because the tin ions, I can use the tin. What's happening to the tin? I'm making more tin ions, but tin is big and heavy. I'm making tin ions and I'm making extra of these, but they're big and heavy. There are smaller ions that could possibly move across there. And those would be in the salt bridge, your potassium ions, and maybe some of your tin ions. And in that way, we would move them towards the chloride side. So your ions here would be your tin ions and your potassium ions. And which way are they going to move? They're going to move towards the chlorine half cell.
I think it's time for a break now, so don't go away. We'll be right back. Welcome back from the break. Let's not waste any more time and get straight back to today's revision lesson.
A strip of aluminium is placed in a beaker, brilliant, containing a blue solution of copper 2 salt. After a while, the solution becomes colorless. Guys, this is really important. The blue solution comes from the fact that we have Cu2 plus ions. If the Cu2 plus ions disappear, that means I'm going to be forming copper metal. The Cu2 plus ions are being taken out of the solution, okay? Then they ask, how would the reading change as the reaction proceeds? Well, the solution changed color all by itself. Because it changed color all by itself, that means it is a spontaneous reaction. So I could essentially, if I set it up right, make a cell out of it. That means it's a spontaneous reaction, which means it would be a galvanic cell, which makes it, it means that it's going to increase, okay? My reading would increase. So it's going to increase. Why? Because it is a spontaneous exothermic reaction. Okay? It will be a spontaneous exothermic reaction because I didn't need to help it. It would happen all by itself. Then, refer to the reducing ability of aluminium to explain why the solution becomes colorless. If we look at our redox table, okay, and remember we use 4B. If you've been taught to use 4A, that's fine. Just go with me with what we're doing. So we started with copper 2 plus. Let's have a look at it. So copper 2 plus is over here. Okay. And we started with aluminium. So let's find the aluminium. The aluminium is over here. Okay. So what is happening is that aluminium, okay, if you look at it, the aluminium minus 166, but it's higher on the redox table, okay? As we go up the redox table, this increases, listen to me, their reducing ability, okay? In other words, the higher up on the table for 4B that it is, the better reducing agent it is. Think that just didn't make any sense whatsoever. Okay. It's a better reducing agent when it's higher up on the table. Okay, so in other words, that it will force the copper 2 plus to be reduced. Okay, because it has a higher potential. It will force it to be reduced because the aluminium is a better reducing agent. Okay, so that leaves us with the next one. Now write down the balanced net ionic equation. Ionic, that's great. That means we can leave in all the charges for the reaction that takes place. So let's go back over here and we start, well, we're going to start with the aluminium. It's the better reducing agent, which means the aluminium is going to get oxidized. And now, just as a little trick, and this is something I do, okay, you might have been taught something different. It's all right. I want to show you something. It's a little trick. And but this only works on 4B, okay? And this is what I tell my learners to do, because it always helps, because often the problem is, I don't know which way to write them. I know, so listen, okay? And yes, I need more sleep. We all understand this, okay? But I always do. Okay, so we're starting with aluminium metal and copper 2+ ions. Unless it is very clearly stated to you, grade 12s, that you have copper 2+ going to copper ions, or copper 1+, because there's another copper equation further down over here, don't use those two, okay? So unless they make it very, very clear in the instructions that you're using copper 1+, ignore those equations completely. You're going to use the copper 2+. So I've ringed the aluminium and the copper 2+, because those are my reactants. That's what I started with inside the container, okay? Now what that means is my aluminium must be written this way around, my copper must be written this way around, and if I join them together, it makes a Z. Some of you might have been taught to see. Everyone does this differently, okay? The fact that it makes this nice Z also tells me that it's spontaneous. So it helps me. It makes me know that this would actually make a galvanic cell, okay? But the aluminium, I need to write from right to left. So it becomes aluminium, becomes aluminium 3+. I'm not sure I could write it any bigger if I tried, but hey, there we go. And the copper is copper 2+ plus 2 electrons. So it's copper 2+ plus 2 electrons, and that goes to copper. But now the question was, write down the balanced net ionic reaction. This is not the net ionic, and it's not balanced, because balanced means that if I add these two together, I sort out all the electrons. So we look at this and we go, well, there's 3 electrons there and there's 2 electrons there. Guys, I have to do something here, because if I just add these together as they are, I'm going to have an electron left over. And electrons can't exist on their own. They can't just run around in the solution and we have this random electron doing whatever it likes, okay? It can't happen. There has to be the same number. So however many electrons the aluminium gives away, the copper needs to take all of them. And we go, this is a 3 and that's a 2, so that means we need to find a common multiple, and that's going to be 6. So I'm going to take my aluminium oxidation reaction and I'm going to times it by 2, and I times everything in that reaction by 2, so that gives me 2Al, which then gives me 2Al3 plus 6 electrons, okay? I'm going to times the copper by 3, because now I get 3Cu2 plus 6 electrons, which then gives me 3 Cu. And why we're doing this is because now we pretend like we've got a maths problem, because over here, and I'm having fun with all the colors today, I don't know if you noticed, the electrons disappear because we've got 6 electrons on both sides, so that gives me 2Al plus 3 Cu2 plus, which then goes to 2Al3 plus 3 Cu. This is a balanced net ionic reaction, and it's balanced in 2 ways. 1, we have the same number of each atom on both sides, and 2, the charge on both sides is the same. 3 times 2, that means this has got an overall 6 plus charge. 2 times 3 overall charge of plus 6. So that's the same. Also, if say they had asked you to put in the spectator ions, which they didn't, but they could have, okay, if I put the spectator ions incorrectly, my overall net reaction will be balanced as well. It's actually a cheat to balancing difficult equations if you can reduce it down to the oxidation and reduction reaction. Okay, now from here, because I know this was my that's not going to help. That's the oxidation, that's the redox. Okay, so I could work out the cell potential if I wanted to, because remember you go cathode minus anode, reduction half reaction minus oxidation half reaction. It's written in 3 ways. You can use any of them. Okay, so this makes it nice and easy. Ionic, leave it as it stands. Okay. If you had got one of the reactions where they have phases, all right, so if we look over here, we got a little bit further down. So over here, for example, if you were dealing with mercury, and you needed to write this equation down. Guys, if you write an equation down from the redox table and it has a phase in it, like liquid, gas, any of those, you must put the phase in. Okay, don't leave it out. Secondly, I needed you to note that's got a double arrow. These are reversible. Watch, when I wrote them over here, arrows in one direction. Okay, my kids have a good giggle when I say that every single time. They go one way. You must make a choice. Okay, and we don't, out of principle, write them going backwards. So we don't write an equation where the arrow goes to the left. We just don't. We read from left to right, so the arrow must go from left to right. Be careful there. Okay. Now, aluminium is one of the most abundant metals on Earth, yet it is expensive, largely because the amount of electricity needed to extract it. Aluminium, always called bauxite. Bauxite is purified to yield a white powder called aluminium oxide, from which aluminium can be extracted, in other words, removed. The diagram below shows the electrolytic cell for the extraction of aluminium at temperatures as high as 1,000 degrees Celsius. Okay, and this is in an iron container. We've got our carbon electrodes, there's a drain, molten aluminium. Now they say, number one, state the energy conversion that takes place in this electrolytic cell. Now, whether you understand the aluminium process or not, it doesn't matter. The point here is that the electrolytic cell always goes electrical energy, okay, to chemical. There is absolutely no exception to that. Okay, it's always electrical to chemical. Is aluminium formed at the positive or negative electrode? So, what we just did is the carbon electrode is your positive. That means the negative electrode is the container. The aluminium comes in through the drain. That means the aluminium is being made at the negative electrode. It's being made at the cathode. So here, it's negative. Okay. Use the table of standard reduction potentials to write down the half reaction for the formation of aluminium. So we go back to our table. We're dealing with aluminium, which is actually what we had over here. Now, in the last question, aluminium was our reducing agent, but this time I'm making aluminium. So this doesn't help me, because what we're actually going to do is we're going to make aluminium. So this time I'm going to go Al3+. So it's over here. Al3+ plus 3 electrons gives me aluminium. Okay, we're doing well. Also, the fact that we've got Al3+ also reminds me that then the aluminium goes to the negative electrode because it's aluminium 3+. It's positive. It's going to be attracted to the negative electrode. Okay? Then explain why carbon dioxide is formed at one of the electrodes. This is just what I was telling you before the break. Oxygen is formed at the anode. Okay? So oxygen gets formed at the anode. The oxygen reacts with the carbon and forms carbon dioxide gas. Okay? And because of the high temperature, that's going to happen all by itself. We do not need any help. Okay? So the oxygen reacts with the carbon because of the high temperatures. So now the question becomes, why should the carbon electrodes be replaced? Well, if the carbon is reacting with the oxygen to form carbon dioxide, it means that those carbon electrodes are actually being eaten away. They are disappearing. So eventually, we have no carbon electrode left for the reaction to happen. Okay. Then, write down the 2 negative effects that the extraction of aluminium can have on the environment. Well, there's actually a couple, but the biggest one is pollution. Okay, this is one of them. And that pollution comes from things like CO2 gas is formed, so it's a greenhouse gas. There's pollution from the production of the electricity needed, especially if it comes from coal. Okay. And the waste, there's a lot of waste. Okay, so the waste product is actually this horrific red mud. Okay, so it's a waste product of mud which has aluminium and all sorts of funny things in it, and whatever was in the bauxite to start off with, that aluminium oxide before it came to us, and that red mud ends up in our groundwater and in streams and lakes and stuff and dams, and it becomes a bit of an issue. Okay, some people, and this of course is, one of those things that can be quite controversial. There can be also noise pollution, though I'm not sure that would be completely defined as an environmental issue. Okay, and wow, we got through that one really quickly. That means we can do the last one. Yay! Okay, last question. No, that's not it. That's it. Yay. So, industrially, chlorine is produced by the electrolysis of brine. Brine means sodium chloride solution. Okay, in addition to chlorine gas, hydrogen gas, and sodium hydroxide is produced. Yay. Write down the equation for the reaction that takes place at the cathode. Guys, this is learn work. All right, this isn't something that I expect you to be able to always work out. This is something you need to learn. Now, it's an electrolytic cell, okay, which means the anode is positive, okay, the cathode is negative, and we learn that hydrogen gets made at the cathode. So now, if you can't remember the reaction, we go back here and we say, okay, fine, I'm putting in water into the cathode, okay, I'm putting water in and I'm getting hydrogen out. Now you can go all the way down your table and look for all the reactions with water and hydrogen. That's the one we're going to use. It's the only one we're going to use. And we learn that we need the OH minus. So I look at this and I go, well, it's 2H2O, so I'm going to put this in over here. So it's 2H2O plus 2 electrons, which then gave me H2 gas. Let's just quickly make sure I've got it right. H2 gas, let's put it in the right phase, plus 2OH minus. Okay, so we're quite happy. Oh dear. Now, write the balanced overall reaction, omitting spectator ions. Okay, now we've got to be careful because the one I gave you earlier included the spectator ion of the sodium. So now we're going, okay, now we're going to go, do they want the sodium? Do they not want the sodium? So now we think about it and we go, well, we know the chlorine's getting made, and hopefully some of you are thinking with me and going, no, I don't know. And the answer is no sodium, okay? No Na+, guys. The reason why I'm not putting in the Na+ is not because I can see it on my answer sheet, but because a spectator ion is an ion that takes parts of the reaction, but it doesn't change its oxidation number. It's a spectator. So the sodium goes in as Na+ over here, okay? It's Na+ over here, and it's Na+ over here, even though it makes sodium hydroxide. Be careful. Be very, very careful. Now, what we haven't done is we haven't actually put in the chlorine. So the chlorine ion, remember, this is what happens with the chlorine. It goes chlorine, okay, becomes Cl2 plus 2 electrons. The nice thing about this is that the electrons are the same on both sides. So my overall cell reaction is going to be the water, okay, plus the chlorine, which then is going to become hydrogen gas, not Hg. It's not going to turn into mercury. That would just be hysterical. Okay, and then I would be worth a fortune if I could make hydrogen turn into mercury. Or not, because mercury is a heavy metal, remember. It's bad for the environment. So we've got Cl2 gas and 2OH minus. Now, what I did with the chlorine wasn't actually needed. It's not what they wanted. All they wanted was that. Okay. And we just check that it's balanced. 4 hydrogens, 2 oxygens, 2 oxygens, 2 chlorines, 2 chlorines. We're all happy. Okay. And I'm going far too fast. Now it says, oh, look at this. Name 2 functions. No, that's the eraser. It's not going to help me. 2 functions of the membrane. Okay, now I didn't actually talk about this. Number 1, it allows the cations to move from the anode to the cathode. Okay, number 1 allows the anion And number 2, it keeps the products separate. So it allows us to collect the hydrogen gas separate, the chlorine gas separate, and the sodium hydroxide. Makes it very easy to collect the sodium hydroxide because that comes out as a solution. Okay, so we've got sodium hydroxide solution, and we still have salt solution. So if we didn't have this separated, okay, this sodium hydroxide would become very polluted. It wouldn't be a nice pure solution, so we would actually end up with sodium hydroxide and salt coming out, which doesn't really help us because then we got the added expense of having to separate them again, so it's got to go through another process before I can put the sodium chloride back through the system. Okay, so it separates them, allows the migration of the cations, the positive ions, and keeps my products separate. All right, now, use the relative strengths of the oxidizing agents present in brine to explain why sodium metal is not one of the products. So, let's just go back to everything we've been using. So we know we're using the water, okay, so we know we're using this. And we said, let's find the sodium metal. Sodium metal is over here, okay. Now, sodium metal, and we've got chlorine down the bottom here. Chlorine, 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 all the way down the bottom, you see. This is a non-spontaneous reaction, and you go, well, you know what, honestly, why shouldn't we get it? The point here is that the water, okay, is a better oxidizing agent. Okay, remember, as you go down the table, the oxidizing agents become stronger. Okay, so H2O is a much stronger oxidizing agent than sodium. Okay, so the H2O is more likely to make the chlorine get oxidized than the sodium, the Na plus will. And because this is a better oxidizing agent, it's going to get oxidized rather than the sodium. Okay, I mean, going to get reduced. What am I saying, reduced? Then, oh, look at that. And last question. Wow, I never have this much time left over. So, chlorine is used in many useful products, such as plastics, drugs, disinfectants, all wonderful things. Remember, chlorine can be also asked in terms of your organic, in terms of the making of PVCs, be careful, polymers. Environmentalists are protesting against large-scale production of chlorine. They base their arguments on the negative impact of chlorine, now careful here, on humans. Okay, guys, be very careful. The question is, negative impact on humans. If you start discussing things like the chlorine gas contaminates water, not enough, okay? Even if in your head you're going, well, if the chlorine gas gets into the water supply, then the water supply is bad, the water supply can harm humans. Guys, you've got to state that. There's got to be cause and effect. So, for example, and I wrote a couple of them down because it just makes it easier, all right? So, first of all, chlorine gas is extremely poisonous. If any of you do history, all right, chlorine gas is the basis of mustard gas. It's what they used in World War I, World War II. It is the most horrific death, okay? It is it's the start of biological warfare. So, chlorine gas is poisonous, okay? Not enough, okay? So, we know it's poisonous, which means, because it's poisonous, and I've got it here, it can cause health problems. Guys, we don't expect you, because it's not a biology exam, okay? So I'm not expecting you to be able to tell me that, for example, if you've ever smelt chlorine, I'm pretty sure you know, especially if like you've done it in a pool, it burns your mucous membranes, okay? So it feels like your eyes and your nose and everything is just burning. It's horrible, okay? But as a gas, it's extremely poisonous, so it causes health problems, okay? Now, there's the next thing. Chlorine gas is actually what is known as a nerve gas, which means it can lead to death. Okay? That's a negative impact on a human. Okay? I'm just saying, it's one of those things can lead to death. The next thing, and this is actually from the memo, they said one of the things they put is that chlorine is used in a lot of drug manufacturing, and of course drug overdosing is bad. I think that's pushing it a little bit in terms of negative impacts. I would go this part. If they had said negative impact on the environment, gets into the water supply, just the environment in general, gets into the water supply, damages fish, animals who drink it, plants, makes the water acidic, all of those sort of things, okay?
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
This one is adapted from the February-March paper in 2009. It says about 1/3 of the protein by humans, for humans, comes from fertilizers. The flow diagram below, that actually makes no sense, but anyway, it doesn't actually matter. The flow diagram below shows 3 industrial processes, A, B, and C, that result in the production of fertilizers. Guys, as soon as they mention industrial processes, that means they're using Contact, Harbor, and Oswald, which means you need to identify them. Now, before we even go to the question, I'm not even going to look at what question 1 says. I'm going to look at my diagram, and I'm going to go, okay, let's just talk about what's missing. Okay, and we're going to go, okay, there's a whole bunch of stuff missing. Let's try and fill it in because they've named stuff, they've left stuff out on the diagram, there's X's and all sorts of things. Spend the time working through the diagram before you answer the questions, okay? So we look at process A, and process A goes to making nitrogen into gas, okay? Now, I just said to you it'd probably be Oswald, Harbor, or Oswald, or Contact, but making nitrogen is not that. I didn't actually mention it earlier. Nitrogen comes from the fractional distillation of liquid air. Fractional distillation, okay? That is still a industrial process, and basically what that means is we take the air that we breathe, they put it under high pressure, low temperature, make it into a liquid, and then slowly heat it up. Nitrogen boils or becomes a gas at about minus 196 degrees Celsius. It's one of the first gases to come off, which means if they keep it at about minus 195, the nitrogen gas slowly comes off and everything else stays in liquid form. Okay, so it's the way we get the nitrogen from. Nitrogen plus hydrogen, that means we're now creating ammonia. That's the Harbor process. Okay, ammonia to sulfuric acid. Oh, no, that's not what they're saying. They're going, the ammonia gets added to sulfuric acid. That means I'm actually going to make ammonium sulfate, okay, because the ammonia reacts with the sulfuric acid and we get ammonium sulfate. Then over here, process C. Oh, look, they even name it for us. The Contact process. Yay, bonus. Sulfur plus oxygen gives me SO2. Now we've just done step 2, so we're going to write it in, which is the SO2 plus the O2, which then gives me SO3. Then we've got SO3 plus H2SO4 gives me unknown, that's the oleum, which means that is H2S2O7, which we then add to the water and get to the H2SO4, okay? So now we look and we go, well, actually, if you were studying from this, this would be a nice mind map to study from. Okay, lots of things from here. In fact, if I was going to do this as a mind map to study from, I would just add in one extra thing is to take the nitric acid across and do the Oswald process to find nitric acid, okay? Do the ammonia. First question, write down the name of process A. Oh, look, we just did that. Fractional distillation of liquid air, okay? We'll pretend you guys can read that, okay? Fractional distillation of liquid air. So we're done, process A, done. Write down the balanced equation for the reaction which takes place in process B. Now they want the reaction for nitrogen, hydrogen gives me ammonia. So this one means we're going to have to write it down balanced. So first thing is we know it's nitrogen plus hydrogen, reversible reaction, okay, gives me ammonia. And then, of course, we need to be able to balance it. So it's N2 plus 3H2 goes to 2NH3. We're nice and simple. Then it says write down the balanced equation for step 2 of process C. So we go back here and look what we did. Look, see, got it. Don't even have to think twice at the moment. So this is the point, is that over here, okay, we now have the SO2 plus the O2, okay, which then gives me, I'm going to write down all sorts of weird and wonderful things there, which is not true, okay, because it doesn't give me anything as to where I was going. So SO2 plus O2 gives me SO3. The most important thing that you're going to forget in this one is the fact that we need vanadium pentoxide. Okay, then it says write down the formula and the name of the product X in process C. So we look and go, well, I actually wrote it down. It's H2S2O7. Okay, H2S2O7. And it's oleum. Okay, or, once again, I'm trying to spell it with a W. Oleum. Okay, I have no idea where they get these names from. I'm just saying. Or we can call it pyrosulfuric acid. Okay, and it's also sometimes known as fuming sulfuric acid, okay? Hopefully we're okay. Then it says write the formula and the name of the fertilizer represented by Y. Now, I've told you already that it's ammonium sulfate, and I promise you, that should be a 2 there. Some of you are going, okay, I don't know why it's ammonium sulfate. Let me show you. So we're going to go back down here, okay? Let's take this off. Okie dokie. I just did it so I can wipe the board. And it's very important to make sounds when you do this. Okay, so we're taking ammonia, NH3, and we adding it to sulfuric acid, okay? This is an acid-base reaction, okay? And what you learned in acids and bases is that we're going to give the hydrogen away, okay? And normally what would happen is if that base was attached to a metal, the metal would attach itself to the anion of the acid, okay? So we would get a salt that was some sort of sulfate and water, okay? But there's no metal attached to the ammonia. So what happens is this ammonia becomes NH4 plus because it's gained a hydrogen. The sulfate, and it would give both away, becomes SO4 minus. And these two are now attracted to each other. So that ends up giving us the salt, ammonium, and I need two of them because it has a charge of +1, ammonium sulfate. Okay, so it's an acid-base reaction, and it gives me ammonium sulfate. So back here, they wanted the formula, NH4 2SO4, and its name, ammonium. Okay, the A turns into an A into a UM, and it's ammonium sulfate.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Please visit our website, learn.mindset.co.za, to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.